Hello, my name is Jamie Tucker-Foltz, and this is joint work with my advisor, Ariel Prokacha at Harvard, and Isaac Robinson, who's now at Oxford. Our paper is an attempt to bring a fair division methodology to the problem of school redistricting, which is when a municipality needs to redesign their school attendance zones such that each zone contains one school, which is where the students in that zone are assigned to attend. And in this example of a school redistricting map from San Francisco, the red lines are the boundaries between school attendance zones, and the red circles are the schools in those zones. And this can be a contentious process in practice for, among other reasons, the fact that not all schools have the same quality, so it's important to be fair. And fair to what is a good question you should ask for this problem. In our paper, we take the perspective that you want to be fair to various different demographic groups, which can be challenging, for example, because say you're taking a demographic group like race, well, students can only be assigned to schools that are close to them, so it's going to have to correlate with geography, and the geography can be quite segregated among the demographic groups. And you might care about other things other than race, such as income level. This is just one example. But in any case, we want to design algorithms that prioritize equality among demographic groups, while also respecting these distance constraints that students should not be assigned schools that are too far for them. And the contribution of this paper is existence results in algorithms for finding proportional allocations that satisfy these feasibility constraints, where we've adopted the notion of proportionality from fair division and modified it appropriately for our setting. And so just a warning before I go much further, that this was the real world problem that inspired our paper, and we're going to take several departures from the real world. And in particular, our model of this problem involves just throwing all of the constraints about geography into a graph that says which schools are feasible for which students. It loses a lot of the information about the problem. And from there, we reduce our problem to a problem from continuous fair division that's a new cake cutting variant, so that we can apply topological non-constructive existence theorems to say that fair allocations exist. And by the end of this process, maybe we've solved saved the entire public school system, or maybe we've just solved a problem that was very removed from the original real world problem that we started with. So if you take that latter view and you're skeptical of the applicability of these results, I will just say for the skeptics in the room, you can view our paper as taking a well-studied valuation class, namely OXS valuation functions, and looking at adding one constraint to this fair division problem, and it makes it quite a different problem than the original problem in terms of what is possible and what is not possible. And so I'll explain what that constraint is shortly. So jumping into our model, an instance of the school redistricting problem is specified by a set of n students partitioned into G disjoint groups. These are the groups we're trying to be fair to, who we're going to treat as players. And we have a set of M schools, each with a value VK and a capacity CK for the school K. A bipartite feasibility graph encodes all the information about which schools are feasible for which students. So in this example, we've drawn little circles around these schools that show the radius of feasibility. If you're in the circle, it's feasible to assign a student to that school. If you're out of it, it's not feasible. And so it's just a bipartite graph, and that's going to be the central object we study. All students must be assigned a school, and given some allocation assigning students to schools, we say the utility of group I is the sum over all students S in group I of the value of the school that S is assigned to in that allocation. And this type of utility function is called an OXS valuation function. It's been studied before without this constraint that all students must be assigned. So that is the new twist that we are putting on this paper. And so for this little toy example, we've got a bad school with I always draw the bad schools and decrepit looking in red, and the good schools all sparkly, shiny, and green. And maybe that has a higher value than the bad school here, this example. And in this particular instance, there are two possible allocations, right? There's 6 students and 6 seats total, because the total capacity is 6. And here's one allocation that the yellow group would certainly prefer, where both of its students get assigned to the good school. And this is the other allocation, which would be preferred by the purple group of students, where one gets assigned, where the good school is divided between the purple and yellow group as much as possible. And maybe we have some intuition this latter one is more fair. On the other hand, it seemed like it was an unfairness out of our control that the purple students just happen to live farther away from the good schools. And this is definitely a problem that we are only sometimes going to be able to mitigate. The main fairness axiom we study in this paper is proportionality. We're going to say that an allocation A is proportional if for any group I, the utility they get under that allocation is at least 1 over G fraction, recall there's G groups total, of the maximum possible utility they can get. In other words, for any feasible allocation A prime satisfying the capacity constraints, they should get at least 1 over G of that utility. And unfortunately, it turns out that proportional allocations do not always exist in this model. And so we're going to have to weaken it in 2 ways. And the first way is that we're going to allow an additive gap in utility of T times the maximal value of any school. And secondly, we're going to have to allow the allocation to violate the capacities by an additive total of T extra seats. Okay, and then the question is, how small can we make T and get proportional allocations? And so here's a counterexample where it's not possible to be proportional, and we can make this an arbitrarily large circle. We have an alternating ring of schools with capacity 1. The red ones are bad schools, think of them as value 0. The green ones are good schools, think of them as value 1. And we alternate bad school, good school, bad school, good school. And we alternate between 2 different demographic groups who can only be assigned to the 1 seat in either neighboring school. So the reason a proportional allocation doesn't exist here is that there's only 2 allocations. There's only 2 perfect matchings in this cycle. And one of them assigns all the good schools to one demographic group, and the other one assigns all the good schools to the other demographic group. And so there's no intermediate allocation here that gives each of them half their utility. One is getting all the utility and one's getting 0 no matter what you do. So it's not possible to be proportional. And using this example, you can duplicate the cycle multiple times with different pairs of demographic groups to show that getting a T proportional allocation might require T to be at least a G over 2. In practice, however, even if there's many students and many seats in many schools, we would expect the number of groups G that we care about to be very small. And in that case, this omega of G lower bound on proportionality that we have is not horrible. We treat G as a small constant. This just says that there might have to be as much as a constant additive gap in the utility that we get for proportionality and a constant number of capacity violations. And indeed, our main result is showing that, yes, we can attain a constant bound just in terms of the number of groups G, not in terms of the other parameters of this problem. Our main theorem is that in any instance of the school redistricting problem with G groups, there exists an O of G log G proportional allocation that can be found in polynomial time for any constant number of groups G. And again, the key fact is that G log G does not contain an N or an M or any of the other parameters of the problem. This is just a small constant depending on the number of groups and nothing else. However, the runtime of this algorithm is not great, is exponential in G. The obvious proof that we have, though we don't see any immediate ways to improve in general, yields a pretty bad lower bound that you get n to the 4th for 2 groups and n to the 10th for 3 groups. As our second main result is complementing this in the special cases of 2 and 3 groups, proving better bounds. We show that both cases can be done with constant proportionality in time n squared log n. And this n squared log n, just to demystify that, that's just the complexity of finding an optimal allocation for each group, which is one of the things that our algorithm has to do. And it doesn't get worse than that. So in the remaining time I have, I want to just say a few words about the proofs of these theorems, and I'll try to give a complete proof of the case of 2 groups, and and some hints of ideas for the proof for 3 groups and the general case as well. So starting for 2 groups, I'm going to use this as a running example, another pathological example, where we've got this checkerboard pattern of schools and students. Every school has 1 seat, and a student can only be assigned to one of the schools it's next to. And notice I'm not displaying any information on the screen about the quality of a school or the membership of a student into which group they belong to. I'm going to abstract that away, and it'll come in indirectly later. All I know is that there are, say, 2 groups, a yellow group and a blue group, and the yellow group, say, has this matching as their preferred allocation. This is the optimal allocation for the yellow group, that if they were doing school redistricting and not caring about the welfare of any other demographic groups, this is how they would assign the students to schools. The blue group, on the other hand, has a different matching that they consider optimal. Perhaps it's this one. And so what we want to do is merge these 2 together to try to find some compromise matching that makes them both at least halfway as well off as they would have been in their favorite matching. And so the first step is we look at them together, put them on top of each other, and see where they disagree. And I'm going to ignore all the schools that don't have any students assigned to them in either matching, and I'm going to ignore all the pairs of school and student. And here we're, by the way, implicitly assuming every school has capacity 1. This is without less generality. I'll just draw this picture differently to assume schools have capacity 1 by just duplicating a school of capacity 10 to 10 schools. And so I'm going to eliminate all the pairs of student and school where the matchings agree. And then all that we're left with has to be a graph of degree 2. And so decomposes into a union of paths and cycles, which have to alternate between the two different colors of preferred matching for the blue group and preferred matching for the yellow group. So I'm going to take these paths and cycles and stretch them out and align them in a line below. And so all I've done is just redraw these paths and cycles. And the key insight of our paper is we can think of this line as a cake to cut, and in the sense of the cake cutting model from continuous fair division. And so we're going to imagine moving a knife from left to right, and we're going to use the yellow matching to the left of the knife and the blue matching to the right of the knife. And as we move this knife, we're going to plot on the left-hand side here the utilities of the two groups if we were to do that. So if we were to use the yellow matching for this cycle and blue matching for this cycle and this path, then these would be the utilities in this example. And here's where indirectly the actual group memberships and school qualities come into play. All I know is that there's some function mapping the knife position into the utilities of the two groups. And with the appropriate normalizations, I can say that when the knife is at the far left edge, we're using the blue matching for the entire time. That is by definition the optimal utility for the blue group. So I'm going to call it utility 1, and I can treat this as a zero-sum game and say that's the worst matching for the yellow group then. And on the right-hand side, of course, the opposite is true. That means we're using the yellow matching the entire time, so the yellow utility is 1 and the blue utility is 0. And so obviously by continuity, there must be some point where it crosses. Of course, I'm using a discrete notion of continuity here because really there are some small jumps in the utilities as I move the knife in discrete positions, but I'm going to think of this as a continuous problem because the ultimate guarantee I'm trying to get is up to some constant times the value of the best school. And so I can think of this as these jumps are small enough that that's going to be wrapped into this fudge factor I have in the ultimate results of the theorem, and I'm going to be able to ignore it on those grounds. And so say that the point where where these lines cross happens to be right here. Okay, so to the right of this, I'm going to use the blue matching. To the left of this, I'm going to use the yellow matching, and both of them are going to get half their utility. This will satisfy proportionality. And the one problem is that if I look at this cycle, what happens if I try to use the blue matching here and the yellow matching here is that both these students might get assigned to the same school, which is a capacity violation. I'm assuming these have capacity 1. And here I'm just drawing the same school up above. But again, I told you proportionality is infeasible, so we're going to have to live with capacity violations, and that's it. There's only one capacity violation because there was only one place I needed to cut the cake. And so in our reduction of this discrete problem to the cake cutting problem, the number of cuts I have to make in the cake is going to correspond to the parameter t in terms of the capacity violations, and also possibly incur some utility loss among groups that you don't get what they want. So that's the full proof for G equals 2 groups, that we can get a single capacity violation and get proportionality. Moving on to 3 groups, we're going to first do this algorithm I just described to find a 1 proportional allocation A between the first 2 groups, ignoring the third group. We get this whole argument I could have done just with a third group there, and they didn't participate in that process at all. And we'll call that allocation A. And then we're going to compare A to the optimal allocation B for the third group and do the same trick. Look at where they differ, or that's the union of paths and cycles, treat this as a cake, and fairly divide it. But now we have to do something a little bit more tricky because we've got 3 different utility functions and we need them to all be the same. And so what we're going to do is, this is my virtual cake. And again, I'm going to imagine placing one knife at the very beginning of the cake, and then we're going to move one of the knives where we're using the purple matching between the 2 knives and the compromise matching A, that was for the first 2 groups, to the right of that second knife. And I'm going to move the knife until I get utility 1/3 of optimal for the third group. And then starting the knife there, I'm going to move it again until I get 1/3, and then again until I get 1/3. So I get a partition of this cake, this continuous cake, into 3 pieces, such that if I use the purple matching just for any one of these 3 pieces, I'll meet the proportionality guarantee for the 3rd group. Okay, the next step is we're going to try to move the knives from this first position, from configuration 1 to configuration 2 continuously, preserving this property that between the 2 knives, if we just toggle that part of the cake, but to use the optimal matching B for the 3rd group, then they get utility exactly equal to 1/3 of their optimal utility, and then continuously move from 2 to 3 while maintaining that as well. And it's not obvious that this is possible to do. And I will say a few words about that on the next slide, but assume for a moment that it's possible to do this. Then if we plot the utilities of the 3 groups, what I've basically said is that throughout this process of moving the knife's positions from configuration 1 to 2 to 3, we're going to keep the utility of the 3rd group constant at 1/3. And then it's not too hard to additionally observe that at positions 1, 2, and 3, it can't be that one of the other utilities is always above or always below. It has to average out to 1/3. And so what that means, again, treating this as a zero-sum game with the right normalizations and definitions of what I mean by putting this utility function as defined between 0 and 1, the picture does really look like this, where we can say that the other 2 utility functions are inverses of each other, and it has to cross the purple line at some point, and we call that our fair division. Say the knives happen to be here, so we'll use matching A here, use matching B here, and matching A here. And again, each one of these cuts, we're going to have a small capacity violation, perhaps a small gap in utilities, but it's a constant number, and it doesn't depend on the size of the instance or any parameters like that. And so that's how we get our allocation for 3 groups. The complexity is big O of n squared log n to find optimal allocations. This is just a maximum weight matching problem, and we need to brute force over the positions of these knives, and that's where we have a dependence on n. Because that's like the length of this cake. So we have to do 2 knives, so it takes n squared time to search for all possible positions where we toggle between matching A and matching B. So that term, the dominant term, is still this n squared log n. Okay, and then the last missing piece is I have to tell you how do we actually move the knives from configuration 1 to configuration 2 and then to configuration 3 while preserving this property that they get the same utility here. And the really weird thing about this is that it's not actually always going to be possible to move the knives in a monotone way. I'm not going to always be able to move them from left to right. It might have to happen that I have to move a knife backwards, perhaps wrapping around to the other side of the cake even, in order to get the knives there. And I actually have to start at the right points to be able to do this at all. And if any of that sounds vaguely familiar from another setting, you may have heard of this problem called the mountain climbing problem, where you have 2 hikers that have to climb this mountain together. One starts at the left endpoint, one starts at the right endpoint, and they have to continuously scale this 2-dimensional picture of a mountain, summiting together and always having the same elevation as each other. And so what happens as they start to climb this mountain is you'll get to a point where one climber may have reached a local peak, and then the other climber has to start climbing downwards in order to allow the other climber to advance. But so this is just in the same way that the knives may sometimes have to backtrack because of how the valuations get toggled around. And then once they're here, then they can summit together and reach the unique peak of this mountain at the same time. And the mountain climbing lemma says that this is always possible. And we actually reduce our problem to the mountain climbing lemma. This turns out to be exactly the tool we need to show that it's possible to move the knives in the way that I hinted at. And we do this through several steps. And one of the steps is reducing to an intermediate problem, which is a variant of the mountain climbing lemma that we've termed the ridge climbing lemma, where you have an infinite periodic increasing function, and you have 2 climbers that just need to climb from -infinity to infinity, while always maintaining the same exact difference in distance on the ridge. And it's the same sort of problems you encounter. And this is just a nice intermediate problem that's closer to our exact setting that we reduced through. So that's the proof for j = 3, all I'm going to say about it. And then I'll just sketch the ideas that are involved in the general algorithm. It's a recursive approach where if g = 1, this is the base case, we just compute an optimal allocation for whatever group we're considering. This is going to be proportional for that group. Done. Otherwise, we partition the groups into two subgroups, each of size g over 2. And then we run our recursive algorithm on both of these smaller parts to return proportional allocations for both subgroups. Then we look at these allocations and then do the same cake cutting trick. We have a pair of allocations, look at their difference. It's a unit of paths and cycles, treat this as a cake. And what is the cake cutting problem exactly that we need to solve? All I'll say about it is that we can reduce our problem to a variant of consensus halving with a twist that you actually have negative valuations for parts of the cake. And so while this, we don't have any out-of-the-box results that you can just apply to this setting, we can tweak it a bit to apply the Stromquist-Woodall theorem to say that a consensus halving exists with these negative valuations. There's also some other twists that make the problem easier and harder. It's not exactly consensus halving with negative valuations. There's a few other things as well. But we're able to apply the Stromquist-Woodall theorem to say that the number of cuts you need is at most 4g minus 2, where g is the number of groups. And that determines the running time of their algorithm. It's all the cost is going to be incurred at the very first step when you're dividing it between considering all the groups. You're going to need 4g minus 2 cuts, and that's going to be the exponent in the runtime because you have to brute force over that many knives. For the t-proportionality guarantee, it's not just the worst case number of cuts we need in any call. It's going to be the total number of cuts because you accumulate this over all the different rounds of recursion. And so by the master theorem, if at every step you need 4g minus 2, I'm creating two subproblems of size n over 2, size g over 2, sorry. So it's O of g log g complexity by the master theorem. And that's where the O g log g comes from. So to conclude, our contributions were introducing this new fair division problem that captures some aspects of the school redistricting problem, not all of them, obviously, and it's a special case of OXS valuations with a twist where we have a constraint that all individuals must be assigned. Our main results were existence proofs, algorithms, and also as lower bound for achieving approximate proportionality. And another conceptual contribution, I think, is just this application of the mountain climbing lemma. It's a problem that people in fair division should know more about, I think, and there haven't been very many results so far. In it, I'm aware of only one, which is where I learned the mountain climbing lemma from, which is by Wesley Pegden and Alan Fries in SOTA 2023. And I hope there are more to follow. If you encounter a continuous fair division problem that you don't know how to solve, this might be a good tool to have in mind. And this is a nice example of it being applied to get improvement in running time as well. For future directions, obviously, it would be great to incorporate more realistic constraints from the school redistricting problem that we started with as our motivation. For example, an elephant in the room is contiguity, which we throw out the window. We don't care about continuous attendance sums at all in this model. It's just, is a student assigned to a school that's close enough or not? That doesn't imply anything about contiguity. Heterogeneous preferences would be another thing to incorporate. We think that some of our results would actually extend to this with not too much difficulty, but well, we didn't bother going down that route for this paper. But it could be a very interesting question for future work, as heterogeneous preferences definitely exist. Also, can we get stronger fairness axioms and proportionality? We did look into adapting envy freeness, and our paper has an impossibility result for a very weak notion of envy freeness that you can look up as well. But it would be nice to have something that actually is feasible that's stronger than proportionality, because it is quite a weak axiom at the end of the day. A technical question is, can we close the gap between the omega of g and the big O of g log g for the t proportionality that exists? And this is not an algorithmic question, it's just an existential question. How many capacity violations do you need? What is the utility gap that you need in order to find proportional allocations with g groups? And just shaving this log factor could be an interesting question. And finally, we have no idea what the runtime really should be. All we're doing is applying these non-constructive existence results and then brute forcing over the parts that we don't know what to do. And so we get pretty bad runtimes. And it's quite possible that a different approach could actually yield a polynomial runtime in the number of groups, which would be very interesting. We have no conjectures on whether this is true or not. Thank you for listening.